Okay, so this is June 2009, question 2 from module 6, and the first part of the question is to outline one potential advantage for nuclear fusion. In previous questions we've seen that the two main advantages that are highlighted are an almost limitless fuel supply, sometimes an abundant fuel supply, plentiful fuel supply, and no long-lived radioactive waste. Those are the two answers. This one doesn't mention it, but in all the others, what was mentioned was the fact that there's more energy per nucleon in the fusion reaction than compared to the fission reaction. Right. The advantages of nuclear fusion are only theoretical because practical fusion reactors are still in development stage. The JET, Joint European Torus Reactor, is a facility of the plasma which is about 100 million Kelvin. What is meant by the term plasma in this context? Well, a plasma is simply an ionized gas. So that means that it contains electrons and ions which are moving around in constant rapid random motion. Okay, the method of confinement then that is used for the hot plasma in the jet is magnetic confinement, and explain why the plasma confinement. Well, why is it necessary to confine? Well, this is to prevent the plasma from touching the walls. So that the kinetic energy of the particles or the temperature does not drop. Alright, why does the plasma temperature need to be so high? Well, that's so that the protons can overcome the electrostatic repulsion. So the protons can overcome the repulsive forces and undergo fusion. So these two particles, the proton and the proton, have to come together, right? They therefore then need to have sufficient energy as they approach in order to overcome the electrostatic repulsion between the two positives. Otherwise there'll be no fusion. Right. The next part of the question involves this particular reaction here. So this is deuterium plus tritium gives helium plus then a neutron plus Q. So Q is the amount of energy that is released, and in this question you're asked to find the quantity of energy released. So we're given the particles, we're given the particle masses, and we're then asked to provide a calculation to show. So what we're saying here is that Q, the energy released, that's equal to the change in energy coming about because of the change in mass, where E equals mc squared, so delta E equals delta mc squared. So that means that Q has to be equal to, well, first of all we have the change in mass, so we have the deuterium plus the tritium, so we've that added together, and we've got this added together, and that's the delta mass, that's the change in mass. So we have to take those, and we're saying, so the change in mass then is going to be the 2.014102 plus 3.016049 minus, and then that's going to be 4.002603 plus 1.008665, right? And that is the mass in mass units. So that then is worked out, and we need to multiply that by 1.67, so that's 1.67 times 10 to the minus 27 times the expression that we have above. So, and then we have to multiply that all by, so it's 1.67 times 10 to the minus 27. Remember, that just comes from the formula sheet, times that delta mass from above, and then we're going to multiply by 3 times 10 to the power of 8 all squared. Fill in those values and you will get 1.7 times 10 to the power of 7 electron volts, which is 1.76 times 10 to the power of so that becomes then 17.6 mega electron volts. We need to remember here, whenever we do that, that gives us our answer in joules. So once we get our answer in joules, we divide that by 1.6 times 10 to the minus 19, and that changes it to electron volts, which gives us our answer 1.76 times 10 to the 7, and that then becomes 17.6 mega electron volts.